When we picture the universe, we usually think of these lonely, bright galaxies just kind of scattered across a huge, empty void. But what if I told you that's not even close to the real picture? Today, we're going to dive into the colossal, hidden architecture of our cosmos and the incredible science that's working to bring it into the light.
So let's just start with a really big question. If you could zoom all the way out, I mean way, way out, what does the universe really look like? It's definitely not just a random spray of stars. It's something way more beautiful and complex.
Well, what you'd see is what astronomers call the cosmic web. And honestly, thinking of it as the universe's secret skeleton is the perfect way to describe it. Picture this giant, sprawling network. You've got these dense knots of galaxy clusters, and they're all connected by these immense thread-like bridges of gas and dark matter. And in between all of that, huge, almost completely empty voids. This is the true map of the universe. And the scale we're talking about, it's just staggering. I mean, look at this. A single one of these filaments stretching for 15 megaparsecs. Now, that's a unit astronomers use for just ridiculous distances. It's almost 50 million light years long. And get this, they recently discovered one that's rotating. This isn't some static old fossil. It's a dynamic, spinning celestial highway for galaxies.
So, here's our roadmap for today. We're going to start with the universe's secret skeleton. Then we'll look at how we see it with radio eyes. We'll tackle the challenge of taming an absolute flood of data, and then get into the crucial fight for dark skies. And we'll wrap up with a peek at astronomy's next generation.
All right, first up, let's dig into this cosmic skeleton. Because it's not just a pretty backdrop, It's more like an active construction site that's literally telling galaxies how to form and how to grow up.
So these filaments act like a kind of cosmic scaffolding. All the matter, all the gas, it flows along them, feeding hungry young galaxies. And we can see this happening. Galaxies actually tend to line themselves up with the filament, kind of like logs floating down a river. And this is the cool part, the powerful jets that shoot out from their supermassive black holes, they point in all sorts of random directions. And that tells us this really fascinating story about how galaxies evolve. It's a mix of both orderly growth along these cosmic highways and this messy, chaotic feeding frenzy at the center. Okay, but if so much of this web is just made of cold, dark gas, how in the world do we actually see it? Well, to do that, you have to look at the universe in a completely different kind of light. You need radio eyes.
This really says it all. Optical telescopes like Hubble, they see the finished product, the bright starlight from galaxies that are already there. But radio telescopes, they see the construction site. They see the raw materials, that cold hydrogen gas that's going to become the next generation of stars. They see the universe's future, its potential.
And a perfect example of this in action is a project called the MeerKAT survey. They're using the ridiculously powerful MeerKAT telescope down in South Africa to take a deep, deep census of the radio sky, all to figure out how galaxies have changed over billions of years. Just check out these numbers from one of their first data releases. In a tiny patch of the sky, just 1.6 square degrees, they found nearly 10,000 separate radio sources. It's wild. In fact, their observations are so deep, they're running into a problem called classical confusion. That basically means there are so many faint, distant galaxies in their images that they all start to blur together. It's a fantastic problem to have. So having all this data is one thing, but turning it into something we can actually understand, that's a whole other ballgame. And that brings us to one of the biggest and kind of unseen challenges in astronomy today, just wrestling with the absolute flood of information our telescopes are sending us. The journey from just a raw blip of a signal to one of those beautiful cosmic maps is incredibly complicated. First, you have to hunt down and get rid of all the interference from our own stuff. Satellites, cell phones, you name it. Then you have to correct for how our atmosphere messes with the signal. But my favorite part is this step they call peeling. They'll find a super bright star in the foreground, create a perfect digital model of it, and then just subtract it, peel it away to see the faint little galaxies hiding behind it. It's only after all of that that you can finally create the image. But even as our technology gets better and better at seeing the faintest whispers from the universe, a new storm is gathering right here on our doorstep. It's the growing problem of pollution. Not just light, but radio pollution from space itself. Yeah, we're talking about the explosion of satellite mega-constellations. For optical telescopes, it's like a vandal drawing bright crown streaks all over your masterpiece, ruining hours of careful observation. But for radio telescopes, it can be even worse.
They're getting blinded by both the intentional signals from these satellites and just the unintentional electronic noise they give off. And, if we look a little further ahead, a new lunar economy could mean the moon itself becomes a dumping ground for old spacecraft.
The good news is the astronomy community isn't just sitting back and watching this happen. They're actively fighting back. They're building smart software to predict when satellites will pass overhead, they're working directly with the companies to design less reflective satellites, and they're pushing for global standards like a zero debris charter. It's a full-court press to keep our window to the universe open.
Okay, so despite those challenges, I gotta say, the future of astronomy has probably never looked more exciting. Let's take a quick look at what's coming next.
The whole field is just buzzing with new ideas. One of the hottest topics right now is something called active galactic nuclei. Researchers are trying to connect the dots between the insane physics happening right at the edge of a supermassive black hole's event horizon and how that can affect gas clouds hundreds of thousands of light years away from the galaxy. It's incredible. And then there's this other mind-blowing area where scientists are using AI and machine learning to study gravitational lensing. You know, how massive objects bend light. They can use it to build these unbelievably detailed maps of dark matter and even get a better handle on dark energy, that mysterious force pushing the universe apart. This is a total game changer for cosmology. But here's a hidden challenge, kind of the dirty little secret of modern astronomy. To understand the light from these distant objects, we rely on really basic lab data about atoms. And you can see here, a lot of our fundamental data for elements heavier than iron, it's based on measurements from the 1960s. For the next-gen telescopes we're building, this old data is the weakest link. We desperately need to update it. And the instruments that need this new data, they're not science fiction. They are right around the corner. Starting in 2025, the Rubin Observatory will begin its incredible survey. The Square Kilometer Array is going to completely rewrite the book on radio astronomy. Around 2030, the extremely large telescope will open its giant eye, followed by the new Athena X-ray Space Telescope. This is the fleet that will define our view of the cosmos for the next half-century. And what are they going to do? Things that honestly sound impossible right now. The ELT, for instance, will be powerful enough to see the individual images of stars as their light gets bent around the supermassive black hole at the center of our own Milky Way. And, of course, they will discover and study Earth-like planets around other stars, sniffing their atmospheres for any hint of life.
So here we are. It's this remarkable moment. We are finally truly mapping the invisible skeleton of the universe, and at the exact same time, we're building these unbelievably powerful new tools to explore it. The map is being drawn, the ships are being built, so the only real question left is, what fundamental secrets are we going to uncover next?